Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, I'll go through this Cambridge International O-level chemistry. This is similar to any IGCSE or GCSE level chemistry, for which 14 to 16 years old students will have learned about organic chemistry as the last bit of chemistry contents in that age group. So here we got formula, functional groups, and terminology. There is a bunch of stuff within the syllabus to go through, but the way to go through about organic chemistry is not to worry too much about each of these points, but to be able to do all of these together by the end of the whole story. So just to briefly go through the syllabus content, candidates should be able to state what is meant by structural formula. If you see this term, give the structural formula, it means you must see the structure. If you cannot see the structure from structural formula, that means, it is not a good structural formula. So in connection or in conjunction with the structural formula, what is the most important thing to take away is that carbon forms 4 covalent bonds. So we know from structure and bonding topics that carbon is in group form. It has got 4 electrons in the outer shell, and therefore it wants to share 4 electrons to complete its outer shell. That is the reason why carbon forms 4 covalent bonds. This is the single most important idea in organic chemistry. Carbon forms 4 covalent bonds. If your carbon forming less than 4 or more than 4, that means your structure is wrong already. And then this is unambiguous, meaning no doubt at all. Unambiguous means you leave no place for people to doubt you because you can see the structure. These atoms are arranged. CH2, CH2, there is a double bond there to indicate that this is a carbon-carbon double bond. So each carbon, they already form 2 covalent bonds. One more to hydrogen, one more to hydrogen. Carbon form 4 covalent bonds, such as this one I'm talking about here. This is not dot and cross. These are called display formula, where I display all the covalent bonds. Each of these lines represent 2 electrons, which you can convert to dot and cross easily. The next bit, CH3, CH2, OH. You can see the carbon form 4 covalent bond, 1, 2, 3, 4, 1, 2, 3, 4. Hydrogen always form a single covalent bond because hydrogen has got 1 electron in its first and only shell. They only share that 1 electron, they form a single covalent bond. Oxygen, on the other hand, 2,6 electronic configuration, 6 electrons in the outer shell. They just want to share 2 electrons to complete the outer shell. Oxygen always form 2 covalent bonds, 1 and 2 there. So that is your ethanol. So these are just CH3, CH2, OH. Last but not least, we also have the other structure. So slowly running out of space there, but I think I should be able to draw what I need to draw. Let me try and do CH3 and then C double bond O, and then CH3. Should be able to make that a little bit smaller. Should be able to make that a little bit smaller as well. Okay. Then we can see that we got some space for this thing here. Carbon form 4 covalent bonds, CH3, C double bond O. This is a characteristic of a functional group that we will call ester later on. But the idea is that structural formula is not display formula. These are what you call display formula because we show every single covalent bonds. That is basically what display formula is. Display formula is show all covalent bonds, including every single covalent bond, especially the one that people forget is O and H single covalent bonds there. Structural formula is not display formula. It's basically a summarized version. CH2 double bond CH2, CH3 CH2 OH, CH3 CO2 CH3 there. So that's it really, structural and display formula. There are some general formulas for alkane, alkenes, alcohols, and carboxylic acids. And I think I'm just going to quickly go through the actual contents in the notes, and they will make sense in terms of the syllabus actually, rather than me going through everything in the syllabus one by one. So carbon is unique, as I mentioned. You can have long chains, you can have long chain carbon atoms, you can have single, you can have double, or you can have triple covalent bonds. So are we talking about carbon-carbon single, carbon-carbon double, carbon-carbon triple? If this carbon form a single covalent bond there are still 3 more covalent bonds that this carbon can form. Already form a double covalent bond, so this carbon can form 2 more covalent bond. Already form triple covalent bond, so this carbon can only form a single covalent bond. You can also arrange themselves in rings. So the simplest ring will be 3-member ring like this. So the idea is that carbon forms 4 covalent bonds. That's the trick again. So when you have a ring, so each carbon is bonded to each carbon. So that means the carbon they already form 2 covalent bonds. Therefore, we are left with 2 hydrogens or 2 remaining covalent bond, and you could see each carbon forms 4 covalent bond, each hydrogen forms single covalent bond. When you add up the total number of carbon, you get C3. Add up the total number of hydrogen, you get C3H6. Similarly, we could have 4-membered ring like this, and then we could talk about carbon form 4 covalent bonds. Similar kind of story. So we could then get C4H8 as your ring, 4-member ring there. So every name in organic compound contains 3 parts. This part of the syllabus is not really about memorizing the whole thing, although there are some stuff to actually remember. First of all, you must find the number of carbon atom in the longest continuous chain. So not part of the branch. It has to be continuous. You have to number it so that you get the longest number of carbon chain. And number 1, this is MIF. These are the prefix. Prefix basically means the name come before. So these are before the actual name. So these are called prefix. So therefore 1 carbon is called METH, M-E-T-H. 2 carbon is called IF, E-T-H. 3 carbon is prop. 4 carbon is bute. So these are the most common one in the syllabus: METH, IF, prop, and bute. There is no way you should get confused between 1 carbon, 2 carbon, 3 carbon, and 4 carbon. Some of the lesser common one, but they do get asked: pent, P-E-N-T, like pentagon, is 5 carbon. Hex, 6-member ring, hexagon. Hep, which 7, so hex is 6, hep is 7, and last but not least, oc is for 8 carbon there. After you find the longest chain carbons, then you need to find out about the functional groups. If you can see alkanes, this is the first bit in these tutorials that you come across this thing called alkane. So it ends with a and e. So you can see the a and e, whereas the next bit is e and e. So there's the difference there. Alkane, alkene. Alkane refer to all carbon-carbon, single covalent bond. Alkene refer to carbon-carbon, double covalent bond. That's the difference there. In terms of other functional groups, we also have OH. OH group there represent alcohols. That's why your name has got all. Whereas we have oic acid. Oic acid refers to this family called carboxylic acid, and we have come across this in the topic of weak acid that only partially ionizes, or they only partially dissociates into H+ ions in solution. So that is why it's a weak acid. The pH is still below 7, but the range from around 4 to 6, something like that, within that range. Or 4 to 7 actually, but I don't want to include 7 there, so that is fine. What is important is carboxylic acid has got the CO2H. Alcohol has got just the OH, like this, whereas carboxylic acid will be whatever group bonded to carbon. You got the CO2H, that is your CO2H. Carbon form 4 covalent bond, 1, 2, 3, and 4. In this OH, the oxygen form 2 covalent bond. You could see the carboxylic acid has the OH group as well, but it also has got this C double bond O, and that's what makes it carboxylic acid overall. Last but not least, we have the carbon atoms of the main chain, the longest continuous carbon chain. We already identified whether it's alkane, alkene, alcohols, or carboxylic acid. And then you want to give the lowest possible number for the substituent and the functional group. So minimize the number for the functional groups or the substituent. This is the last bit that's very important in the name. We have the next bit, which is basically if you have more of the same substituent group. If the same substituent group, this means repeated substituent, so they are the same group. So di refers to 2 times. How about tri? Tri refers to 3 times. Last but not least, tetra is basically, oops, let me just circle that properly. Tetra refers to 4 times of the same repeated groups, and then you must put in the positions indicated by numbers. So let me give you a couple examples. Maybe we'll give you the example later on actually. So what is functional group? Functional group is just the atom or the group of atoms, and it determines the chemical properties of a homologous series. This is the first bit that you must come across. So functional groups is this atom or group of atoms that govern the whole chemical properties. So all the alcohols will have the same properties, all the alkenes will have the same properties, all the alkanes will have similar properties. On the other hand, you have homologous series. So this is another definition. What is meant by functional group? What is meant by homologous series? Homologous series is basically the family of the similar compounds. I think what I described was actually homologous series, but as you could see, they are related, functional group and homologous series. So homologous series is that family of compounds that have the same chemical properties because of same functional groups. Now, what do they like to ask you? They like to ask you what are some of the properties or characteristics if you have the same homologous series, you have same functional group, same general formula, and you only differ by CH2 unit. And if you differ by CH2 unit, you have 12, you have 2 times 1. So this is a difference in mass, difference in MR by 12 plus 2 times 1, which is 14. And this is a result of adding more and more CH2. So you add more of the CH2 like that, because you have left and right, which you could extend as part of the chain. So this is called adding CH2 there. So there is a trend in physical properties, such as boiling point would increase as the number of carbon increases, but similar chemical properties. So if you are alkenes, they all behave the same way because they all have carbon-carbon double bond. If you are alcohols, they all behave the same way because they all have OH. If you are carboxylic acid, they are all acidic because they all have CO2H. This is a trend. This is not similarity. So there is a trend such as boiling point, melting point increases with more carbon in the same homologous series as the intermolecular forces get stronger and stronger. Just to run up what we have done so far, homologous series is that family of compounds, similar chemical properties as a result of same functional group. Okay, so alkane, alkenes, alcohols, and carboxylic acid. We have the name ending in A and E, alkane, alkene. And then we have alcohols. Alcohols end with OL. Carboxylic acid end with oic acid. So you will have methane. You have just now earlier. Meth for 1 carbon, eth for 2 carbon, prop for 3 carbon, bute for 4 carbon, and so on and so forth. Meth, eth, prop, bute, 1, 2, 3, 4 respectively. You have methane, CH4. You have ethene, because you must have carbon-carbon double bond. So minimum is 2 carbon, because to have carbon-carbon double bond, you need minimum 2 carbon. So you cannot have methane. So you can only start with ethene with 2 carbons. There will be C2H4 based on the general formula. Just to run up this session, how in the world do we come up with this general formula? If you think about alkane, so if you have alkane like this, that means you will add in hydrogen, 1, 2, 3, and 4. So these are 2 carbons, single covalent bond because it's alkane. I add in 1, 2, 3, and 4. Carbon form 4 covalent bond. So altogether, I am going to add 2 more, 1 there and 1 there. For each carbon, so the n number of carbons, I will have 2 times the multiple of hydrogen, so it's 2n. But because this is single bond, I can have carbon forming 4 covalent bond, so I add in another hydrogen. Carbon form 4 covalent bond, I add in another hydrogen. That's why there is the plus 2 there. So the plus 2 there refers to this as well as this. Hence, you have the 2n. For each carbon, you have 2 times the multiples of hydrogen. You add the 2 at the terminal there. So starting from n equal to 1, you will have things like CH4, C2H6, C3H8, and so on and so forth. This is for CnH2n plus 2. That is for alkane. Next up, you have alkenes. Alkenes are CnH2n because you have carbon-carbon double bond. So if I have this one just now, carbon-carbon double bond, minimum of 2 carbons. So I'm just going to move this around a little bit. So carbon already formed 2 covalent bonds there. So that means this carbon only left with 2 more covalent bonds because 1, 2, 3, and 4 covalent bonds around this carbon. Similarly, I would add 2 more hydrogen on there because 1, 2, 3, and 4. So altogether, with this alkene carbon-carbon double covalent bond, we can see 2 carbon. For every carbon, there's 2 hydrogen. So it's CnH2n, but it's not plus 2 because you already have a double bond. You cannot add more hydrogen atoms onto the carbon there. Next up, we have alcohols. Alcohols will be CnH2n plus 1 because you replace 1 hydrogen of alkane with OH. So imagine just now we have the alkane like this, and we take away one of the hydrogen at the end there. So instead of 2n, we only have, instead of having the plus 2, we only have the plus 1. We remove the H and we add in the OH there. That is why it's CnH2n plus 1, because you replace one of the hydrogen at the end, whichever one, with OH. We can also talk about the same thing with the replacing the COOH. So here is with COOH. So this is H of alkane. So everything comes down to, you know, drawing it out and seeing for yourself. Alkanes is the pretty clear one. So 2 times the amount of hydrogen plus 2 at the end as your cap. You remove the 2 hydrogen at the end as your cap. Due to carbon-carbon double bond, you get CnH2n. And then from the alkane, you remove or substitute one of the hydrogen at the cap there, at the ending cap. And you replace with OH, you get alcohol. Replace one of these hydrogen with COOH, you get carboxylic acid. The thing about carboxylic acid is because this one has got a carbon there already. So the simplest carboxylic acid is for 1 carbon total. So this is 1 carbon total. If we draw, we can see COOH, but we already have 1 carbon from 4 covalent bond, 1, 2, 3. So I'm just going to add in another hydrogen like this. And you can go on and so on and so forth. If you got 2 carbon, then that is ethanoic acid. This is methanoic acid for 1 carbon. 2 carbon, then I will add in another carbon. And carbon form 4 covalent bond. This carbon is happy, 1, 2, 3, and 4. But the other carbon is not complete yet. So I'm going to add in that. That is called ethanoic acid there. Whereas the other one on the right hand side is called methanoic acid. I haven't really named so much alcohol yet, but methanol will be 1 carbon. So you will have CH3OH. This is from year 9, structure and bonding. As part of the syllabus in year 9, structure and bonding, drawing dot and cross for methanol. So this is methanol. And then you can also draw ethanol as well if you want to. So you can have CH3 because C2H5, because 2 times 2 is 4 plus 1 is 5. So I'm going to show you the structural formula. CH2OH, this is ethanol. If I want, I could have used the formula straight away, and what I would get is C2, so C2H5OH. But the way we think about C2H5OH, you can't really see much. This is the structural formula, showing you the carbon is bonded to 3 hydrogen, another bond to carbon, 2 hydrogen there, another bond to OH, and that gives you the 2 carbon alcohol, ethanol, methanol, and so on and so forth there. Okay, So alkanes are simple hydrocarbons. Alkanes have no functional groups, but the functional group of alkene is alkene. For alcohol is alcohol. Carboxylic acid is carboxylic acid. Alkanes do not have functional groups. If you have the same functional groups, that is because you have you are the group of atoms that determine the chemical properties of that homologous series. So really, we can kind of like, most people actually interchangeably use homologous series and functional groups, but then when we talk about alkanes, we are not really talking about the functional group. We're really talking about the homologous series, because they are just a family of compounds having similar chemical properties, CH4, C2H6, C3H8, because they have similar same general formula, same functional groups. They are different by CH2 unit, a mass of 14, similar chemical properties, but their physical properties are slightly different. There is a trend to it. I'll leave it there for this first tutorial on organic chemistry, and we'll continue to talk more about organic chemistry in our next set of tutorials. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. There's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected.